All right, we are live. Hello, everyone. Welcome to our live stream for September 20th, 2022. My name is Matthew. I am one of the course staff for our online courses. We also do our textbook and all sorts of great stuff. We are happy to have you here. I'm going to let Professor Impey introduce himself, and then we will get started with your questions. Post those questions in the chat on YouTube. We will grab them from there. There's also an email address. If you scroll up to the top of the chat, you can find the email address where you can send those. If you prefer not to ask in the chat, please ask those questions only once. We see them. We just tend to jump around and there's a little bit of a delay and we take email questions, but we do see those questions and they will get asked in hopefully the order that they're provided. So Chris, why don't you go ahead and say hello and then we'll get started.
Okay, welcome everyone to the Q&A session for the online courses and for anyone who found this channel. We'll just get started right away because I have to finish slightly early today.
Excellent. The very first question is from Pinoclean, who would like to know if you can talk about the role of gravity and electromagnetism in the formation of gas and dust in the interstellar medium. What other forces could affect this process? For example, light, since it bends space-time, or static electricity. Can you just talk about that process?
Sure. So the interstellar medium is a very thin medium. The density, it varies, of course, enormously because there are clumps and so on in places eventually where stars will form. But the average density is about 1/10 of an atom per cubic centimeter. So that's about 10 billion times less dense than the air you're breathing. So it's a pretty good vacuum. Most of that material is hydrogen and helium atoms, the primordial material of the universe. And then there are small amounts of dust grains that are either silicates or carbon-rich material. So the interstellar medium is basically gas and dust, very diffuse. As such, it of course is subject to the law of gravity. And so over long periods of time, millions or even hundreds of millions of years, it will clump gradually. And that's in fact how stars sometimes form, from very slow gravitational condensations in the interstellar medium, starting with a small inhomogeneity or density enhancement that gradually accentuates. And then you get a runaway effect when the density gets to a certain point. And electromagnetic forces can also be important because the material is being irradiated by stars that are embedded in it or nearby. Some of it is ionized, and so it's electrically charged material. These are free electrons and free protons, and so they're subject to electromagnetic forces. But the general dominating force is, of course, gravity in terms of creating structure in this medium.
Excellent. The next question is from Demetris. In a hypothetical scenario of a spaceship orbiting a silent black hole, meaning there's no accretion disk in a stable close orbit, could Hawking radiation still be harmful to the crew?
No, I think Hawking radiation, and it's a hypothetical effect because it's never been observed. The theory of Stephen Hawking that predicted it has not been refuted or superseded, but it is still just a prediction. The level of Hawking radiation is truly tiny. So the radiation pressure that results from that is tiny, almost unmeasurable. The temperature that results from that is like 1/100000th of a Kelvin for a solar mass black hole. And so any physical macroscopic object like a person or a spaceship will simply not experience any real effects from Hawking radiation.
The next question is from Christina, who's on with us live. I'm not sure that the premise of the question is accurate, but we can address that as well. So if some lasers seem, in quotes, to be faster than light, would they behave any different for a hypothetical observer approaching a black hole?
So, the theory of relativity, special relativity, does state the light speed as being an absolute limit, and that's been held to be true. Now that means signal velocity. So carrying a signal, photons, of course, can carry a signal. So that means a light beam that's laser light is limited to that speed. Now, it is possible to arrange for a phase velocity to be larger than the speed of light, but no information is directly carried by that. So generally, there's no faster than light speed possible. And remind me of the context of the question or the application of the question. I missed the second half.
Sure. So the question is, would a laser that seems to be faster than light behave any differently when it's approaching a black hole to an outside observer?
No, I mean, to an outside observer, if the laser beam was being fired away from the black hole, the observer would see the light to be gravitationally redshifted. And the closer the laser got to the black hole, the stronger the gravitational redshift, until at the event horizon, the gravitational redshift becomes infinite. The photon loses all its energy and, of course, isn't escaping the black hole. So regardless of the source of the light, whether it's a laser or a light bulb or just a glowing object, the photons near a black hole behave the same way.
The next question is from Hernan Reyes, who sent an email. The Galilean moons, Io, Europa, and Ganymede, are all three in a state of Laplace resonance. So it seems kind of convenient, but how is it that these resonances so conveniently occur? How do the revolution times for each moon so coincidentally fall into a multiple each other? And how does it block them together?
So Laplacian resonance or resonance orbits are not really accidents. They occur because objects are in close proximity to the object that dictates the gravity. So these three moons have ratios of orbital periods of 1 to 2 to 4. So it's a classic Laplacian resonance, i.e. the ratio of whole numbers. And it's because those are three interior moons, small mass moons to a large mass planet. The resonance phenomenon is essentially a reinforcement phenomenon where when two objects have orbits that are multiples of whole numbers, they experience the same phase of push and pull, especially since the orbits are elliptical, so the strength of gravity varies through the orbit. And so these effects reinforce each other over time, and the objects stay in that fixed pattern. Now, orbital resonances can be stable, as we believe the Jovian moon orbits are, or they can be unstable, and then the moons are driven away from the resonance ratio. So there are some orbital moon orbits that are in near resonance. They're not entirely whole numbers, but they could have been in resonance in the past and been driven out of resonance because it was unstable. So there are all sorts of variations. There are exoplanets. There's a chain, I think now, of 5 exoplanets that are in resonance orbits ratios, and actually the TRAPPIST system, all 7 planets are in a resonant chain, which is an extraordinary situation that we don't see anywhere else in the universe.
So that brings us to kind of a follow-up question to that, which is in his question he makes, in his later question, he makes an assumption that the 4 rocky planets of our solar system are obviously not in any form of resonance. So is that true? Are the rocky planets in our solar system in any form of resonance? And how close or far apart do planets need to be to get into a resonant framework?
It's a completely variable scheme, so there's no fixed rule of thumb, but it is true the inner planets in the solar system are not in resonance or anywhere near resonance. Actually, Uranus and Neptune are very close to a resonant ratio, but they also have varied that over time. And so planets can come in and out of resonance over time. And of course, sometimes the reinforcement is such that a planet gets ejected from a system because of that. When the cumulative pushes, because of the phasing up of the enhancement of the gravitational push and pull, that can lead to an unstable effect where the planet is ejected. So only in the case of the 2 outermost planets do we have something close to an orbital resonance. Generally, the planets have to be, or the objects in resonance have to be relatively low mass compared to the object driving the motions, and they have to be fairly close to it. And that's not true, of course, in the inner solar system.
And then the last question in this chain is, actually, you answered it already. Are any exoplanets resonant with each other? And can that be detected? And you talked about TRAPPIST system. Are there others that are similar that we've detected?
Yeah, there are a dozen or more exoplanet systems because we know many exoplanet systems where there's more than one planet. Like I said, the most extreme version is the TRAPPIST system, where all 7 Earth mass planets are in near resonant ratios. That is to say, they're not the ratios of whole numbers, but they're close to it. There is a chain of 5, and I don't remember the exoplanet name, that are in true resonant ratios with whole numbers, and that's the highest number among exoplanet systems.
Excellent. Wonderful chain of questions there. Thank you. So let's see here. Oh, Rentgen 101 had a very similar question, which I was going to do, but since we've answered pretty much all of these resonance questions, I think we'll move on to the next one from Jim. How do we determine the velocity and direction of a star, say 45 light years away relative to our sun?
That represents a solar neighborhood. 45 light years is fairly close. And so for those stars, we can use direct methods, parallax. So we have the Gaia satellite, and we've had Hipparchus before that, which have been able to measure direct parallax of stars. And that's triangulation by geometric method, and that gives you a distance. And then you have proper motion, which is the amount they appear to move on the sky, which gives you a transverse velocity. And then you can measure a radial velocity through the Doppler shift. So if you have a distance, a transverse velocity, and a radial velocity, you pretty much have the 3-dimensional motion. And that we can typically do for stars less than 100 light years away.
Excellent. David Gold would like to know, how does the measurement of the Big Bang cosmic microwave background radiation net out, or how do we see it through the radiation that is coming in from the Van Allen belts or other, conflating sources of radiation?
So there are backgrounds that have to be taken into account when you're dealing with the microwave background from the universe, but it's at that temperature and that wavelength. These are millimeter waves, radio waves, or submillimeter waves, and the temperature, the effective temperature in a black body is 3 Kelvin. Van Allen belts have much higher energy and much higher effective temperature, so you really they're not a contaminating fact. The major contaminating signal for looking at the microwave background radiation is the emission from the galaxy itself, from hot dust and gas, especially hot gas, in the disk of our galaxy. And that represents a significant contaminating signal, and that has to be very carefully modeled and subtracted out.
Francine Kaplan asks, Professor Impey, how have the recent findings, I'm guessing she means JWST findings, but maybe it's more broad to recent research, but have the recent findings aided in your astronomy specialization and research? And how is the University of Arizona benefiting?
Well, starting with my university, it's benefiting enormously because we have a very active and powerful astronomy department, one of the top ranked in the country and even the world. We also have the PIs of 2 of the 4 James Webb instruments, Marcia and George Brieke, and so they have a lot of principal investigator time as the designers of those instruments, sort of guaranteed time. And they form teams with lots of postdocs and grad students. So there's dozens of scientists at the University of Arizona who are benefiting from James Webb observations. I haven't directly benefited because I haven't applied for time on the James Webb. I would well do so in the next cycle. The first cycle is, of course, intensely competitive because everyone wanted to get their hands on this telescope once it's proven itself. So my research hasn't directly benefited, but all around the corridors and everyone in my building is extremely happy with the quality of the data they've seen.
Excellent. The next question is from Ayub Babur, who would like to know, I hope you're well. Is it possible to communicate and transmit information through gravitational waves? And if we could, would it be faster than the speed of light?
We do not have the technology to do that. So in principle, it's possible to imprint information and send it as gravitational waves, you'd actually have to be able to essentially alter mass distribution, because it's when a mass distribution or mass configuration changes that gravitational waves are emitted. And the dramatic examples that LIGO's detected are, of course, merging black holes, which is a very extreme form of mass reconfiguration. So we need some technology to be able to reconfigure mass quite dramatically and somehow code it into gravitational waves. It's possible in principle, and maybe in the far future, humans will have that technology, but I'd say we're very far from that right now. But according to general relativity, these signals, these space-time ripples, if you like, are moving at the speed of light, not faster than the speed of light. So there's no violation of causality with gravitational waves.
The next question is from David Wismer. If you and I could simultaneously determine the state of a wave function of every particle in the universe, what percentage would be collapsed versus not collapsed? And would we get the exact same answer?
It's a hypothetical question about a very hypothetical experiment. I mean, in principle, if you observe a particle in the standard mode of quantum theory, you collapse the wave function and therefore observe the particle to have a fixed measurable energy and position and momentum. Simultaneously observing the properties of all the particles in the universe is not possible even in principle or in theory. So the question is unfortunately so hypothetical as to not be meaningful as an experiment. But if you were measuring multiple particles simultaneously, then again, according to quantum theory, they're independent entities and their wave functions would collapse simultaneously as you made the measurement. And so you would determine fixed parameters.
Excellent. The next question is again from one of our live participants. Let's see. I am human being 3. Would like to know if you can recommend a book that talks about scalar and vector fields as it relates to astronomy.
That's tricky. I haven't taught a course like that for a while, so I'm going to punt on that question basically. But you're looking for a graduate level textbook in astrophysics at this level, so or possibly a senior level undergraduate physics text. Astrophysics text might include the discussion of vector and scalar fields, but it'll be a sort of parenthetic or short treatment, so not a full derivation.
Excellent. Yeah, so no popular sources on that topic, I think. The Center of Astronomical Research would like to know if neutron stars are collapsed, how is it classified as a star without fusion?
Well, I mean, it's a good question. It's really semantic. So stellar remnants or stellar corpses are not formally stars. So we should actually preserve the word star for an object that is generating energy by fusion. So a neutron star formally is not a star in that sense. But we use that designation and the adjective of neutron just to describe the fact that it's a star that's made of pure neutron matter. So it's basically a descriptive term rather than a fully accurate term.
The next question is from, let's see, KP. Can we use an air pressure rocket I'm sorry, hang on. I'm trying to interpret the question too quickly. So I guess the question is, can we use an air pressure rocket instead of a rocket with explosive fuel? What are the limitations on using something like that to get into space or for space travel? Using pressure as opposed to something combustible.
I mean, it's a reasonable question, but I think when you look at the physics of it, you can indeed, of course, generate thrust from pressurized gas. As the pressure is released through a nozzle, say, that gas will go towards the ambient pressure outside and it will create thrust. So it's a mechanism that can work, but it's far less efficient than combustion because at some point the gas that's been held under pressure will just reach equilibrium. And once you've exhausted it and it's each reached equilibrium where the internal pressure in the tank is the same as the outside pressure, then you have no more thrust. You can get a little more pressure if that gas has been pressurized so much as to become a liquid. That helps you a little bit more, but it's still a minor amount compared to combustion, which is gaining energy from rearranging the chemical bonds and the electrons in combustible material, and that releases a lot more energy than just simple decompression.
All right, the next question is from Ramesh. How would we prove the presence or absence of life on Enceladus or Europa? And what are the current NASA projects and timelines on this kind of a project?
The timelines are long because these are difficult missions. These are distances of over 1 billion miles, and they're typically development time of 10 years and a travel and experiment time of 10 years. We're talking 20 years to do these experiments. And both Europa and Enceladus have projects that are in preparation. With Europa, it's from the NASA and the European Space Agency. Enceladus has some very distant plans from NASA, but also has a private consortium that are hoping to go to Enceladus and look for life. So again, all these missions are far off because they're expensive, difficult, and it's a long way. The probability of detecting life or the ability to prove that life doesn't exist, that's very difficult. Proving a null hypothesis, proving that life does not exist somewhere, assumes that you can exhaustively search for life, not just the kind of life you know, the kind of life we have on the Earth, but alternative life, forms of life, because it may have a different biochemical basis. And that's extremely difficult. I mean, even in principle, I don't think we're ever going to be able to prove that a body like Enceladus or Europa don't have life. And so we're left with the experiment of how do you best detect life if you think, for example, it's like life on Earth. And that's typically how we approach it. We assume that it's carbon-based. We assume that it's going to use nucleic acids and store information in some form of molecule, if not DNA or RNA, a close relative of them. And we are looking for metabolism based on the genetic storage of information. So that's how these experiments are going to be designed. And to see something that's radically different is sort of beyond our technical capabilities.
Next question is from Birhane Telena. Can a wormhole be the best option to travel in space?
It could if they existed. So I'll just put the huge caveat right up front. Wormholes are hypothetical constructs. They do potentially exist within general relativity. Our gravity theory does accommodate the possibility of tunnels in space-time from one place to another, and that's essentially what a wormhole is. But then it becomes a question of whether such entities or artifacts of gravity exist in the real universe, and there's no evidence that they do. The signature of a white hole or wormhole will be a little hard to detect, but we see gravity situations that are mostly fairly simple. We don't see convoluted space-times with the curvature that would lead you to think there could be interconnected regions, such as in a wormhole.
The next question is from Faisal. Why do we not yet see the effect of dark matter on the distortion of space-time as happens with black holes and supermassive stars?
Well, I mean, dark matter does distort space-time. So, and so in a sense, we do see the effect of dark matter. Dark matter outweighs normal matter by a factor of 5 or 6. And when you look at a gravitational lensing situation, of which there are many now, galaxy lenses and quasars multiply imaged and so on, again, most of that bending and most of that gravitational distortion is coming from the dark matter. And essentially, we're making a dark matter map of the lensing object. So we do indeed use dark matter, and we detect gravitational lensing by it, and we use that to weigh galaxies and clusters and demonstrate that most of their material, this material that holds them together, is in fact invisible and therefore dark matter.
The next question is from the Center of Astronomical Research again. Can a massive neutron star have an internal event horizon?
No, neutron stars are objects that are below the limit at which point you can create an event horizon. That limit is basically around 3.5 times the mass of the sun. The exact number depends a little on the equation of state of the neutron material. So it's not an uncertain number, but it depends on your model. But it's roughly 3.5 times the mass of the sun. So for an object less than that, that's a stellar corpse, there is no event horizon. You simply have extremely dense, pure nuclear material.
So that is an interesting concept. I mean, during that cusp of changeover, is there such a thing as an event horizon that could like form inside of a star, or as soon as you have an event horizon, it's officially a black hole?
Right. So an object that's not a black hole could turn into a black hole if it were somehow compressed or collapsed any further. Then it would create a black hole, but it wouldn't be creating an event horizon within the material itself. It's just the reconfiguration of that material by shrinking would give you an event horizon at a smaller distance, but it wouldn't be inside the object.
Excellent, thank you. Sunaya asks, is it possible for really tiny black holes to have formed on Earth a long time ago, naturally, long enough ago when we didn't have methods to detect them?
It's certainly possible to have primordial black holes. So it's tiny black holes, that is, black holes that are much smaller than the mass of a planet or a star, macroscopic objects, kilogram black holes or gram-sized, gram-mass black holes. Those are possible in principle. And in the early universe, the density was high enough, the very early universe, the density was high enough in principle to create many of these tiny black holes. Just due to the enormous pressures and densities just after the Big Bang. And those are primordial black holes, and the theory of Hawking radiation suggests they would evaporate very quickly. So there's just one small mass window of primordial black holes that might survive to the present day. And if those primordial black holes, the ones that could survive, were present in the universe, yes, they could be present on the Earth too. We've seen no evidence for their existence, and the limits on primordial black holes are not absolute to have ruled them all out entirely, but they're getting pretty tight. So there's no good evidence that primordial black holes exist, even though they could in principle.
Well, the next question is from Ping Ponger. Is there light in space? So but specifically someplace in between rocks where it's not just dark, but also light, like at the dawn or aurora? Like, can light just sort of exist in the middle of space, or be emitted from the middle of space?
Light needs an origination. Light needs a source, and so the only light we see in the universe is light that had an original source, and typically that would be stars. So most of the light we see in the universe is starlight. Now, starlight over the age of the universe, 14 billion years, will of course have traveled through space and filled large regions of space with photons. So we certainly can see the vastness of space with light in it, radiation in it, very diffuse and very low energy because space has expanded so much. But yes, that light can exist, but it always had an original source.
The next question is from Yang, who asks, do chained collisions in the universe pose any danger to the existence of humanity in a quantitative sense?
I'm not sure what the chain collisions phrase means, but if it means, situations where, a dense set of objects experience multiple collisions or sequential collisions, then yes, I guess if they were stars and they had surrounding planets, that could hugely jeopardize the life on those planets. So those kind of collisions are only possible in very dense regions. In general, the distance between stars or between planets in a star system or the next star system are so great that the odds of collisions are very low. So collisions are actually quite rare in astronomy.
Excellent. Terang has a specific question, but you can talk about, I think we can talk about it generally. So they'd like to know, if two black holes collide with each other, could they form a wormhole? But could you talk generally about what happens when two black holes collide with each other?
So the general idea, which has been validated by simulations that involve full three-dimensional general relativity using supercomputers, and they've been affirmed, of course, by the observation of merging black holes with LIGO. So this is an area where the simulations, the pure theory from gravity, and the observations all agree. So we think we know pretty much what happens when black holes merge. And when black holes merge, essentially the black holes combined masses, some fraction of the binding energy of the gravitational system of two objects is released, as gravitational waves. And the two objects combine to give a mass of a combined black hole that's very slightly less than the sum of the two masses that went into it. There's no indication in simulations or in the real observations from LIGO that two black holes collide and create a wormhole, and there's no necessity or indication that they would from theory, and we don't see it in observation either.
The next question is from an email. VJ asks, why is the telescope image of the sun round or spherical in shape rather than some other shape?
Well, gravitating objects or self-gravitating objects that are held together by their own gravity will take the sort of most energy efficient configuration. And since gravity operates symmetrically in all directions, then the most symmetric object is going to be one that experiences the same gravitational force in all directions. And that's a sphere, the most uniform and the most symmetric object possible in 3 dimensions. So everything from stars to planets will form spherical objects. Objects that form that are not spherical, like galaxies themselves, is because something else is going on, like angular momentum or some other force that's operating.
The next question is from Eliza, who asks, how is a singularity possible? Yeah, but we can just stop there.
Well, singularity is a tricky concept from relativity. It's a problem because a singularity essentially means a cusp of density where the density goes infinite. Infinite mass density is a meaningless concept. Any physical quantity is not representing physical theory correctly. And so the fact that general relativity predicts a cusp of density at the center of a black hole is a problem. It means the theory is incomplete, and this has been known for 50 years. So I would have to say that a singularity is a bug, not a feature of a black hole, and we still haven't fully understood what the meaning of that is. It means we need a better theory of gravity to explain what happens inside a black hole.
So we don't really know how singular is singularity, because we can't measure that.
The word singularity just means cusp, mathematical cusp. So it means an infinite, a spike of infinite mass density. So infinite, and since infinite is not measurable and infinite is not anything that results from any normal physical process, it's a sort of nonsensical result. It's a mathematical result, essentially.
So I've heard of this idea before as well, but Berhane asks, can dark matter be just another galaxy in another or a higher dimension?
We don't know what dark matter is, but we have some pretty good ideas at this point. We've been studying dark matter indirectly and directly through lab experiments, trying to detect it for decades. So it's unlikely, even though there are theories of multidimensional universes and brain universes and so on, based on string theory. These are very hypothetical, theoretical constructs. There's no indication that you need to invoke them to talk about dark matter. Dark matter coexists with normal matter. It explains the rotation of galaxies. It explains how galaxies move in a cluster. It explains how stars move within a galaxy. It explains a lot of the motions we see in astronomy without having ever to invoke a shadow universe or a parallel universe or some other space within which the dark matter exists. All the evidence is that the dark matter exists in our space, in our universe, and it coexists with normal matter.
KP would like to know, is there any chance that we could find another Homo sapien type creature on another planet just like us?
Oh, well, sure, it's possible. I mean, it's a matter of probability, what you think happens on other planets. So the numbers are impressive. We know of about 20 billion habitable Earth-like worlds, that is, worlds that are terrestrial planets with all the ingredients for life. They have energy, they could have liquid water, or if they had water, it would be a liquid on the surface. And there's been plenty of time for biology to occur. So with 20 billion potential biological experiments, it's entirely plausible that on some fraction of them, advanced creatures would have evolved. Biologists tend to think in terms of contingency and convergence. Convergence, the evolution of multiple strands of life that resemble each other, such as eyes in the octopus and eyes in humans, even though in detail they're different. So that's convergent evolution, but contingent evolution is a strong idea, which just says that different species evolve in different directions over time. And so in our one biological experiment, we have many, many branching points of evolution. And so the odds that in a different biological experiment, you'd end up with something that's like any of our species, not just Homo sapiens, but that you end up with anything like a butterfly or an elephant or an orca, are very low. The odds are you'll have creatures, you'll have biology, and those creatures will be very different, and we simply don't know how different.
The next question is, why is it that Jupiter, with so many moons, is classified as a planet and not really thought of more as a small star?
Well, Jupiter does have a lot of moons. It's over 50, I think. I mean, if you go down to the small moons, it may be 70 or 80. They're all very small, though. If you add up all the mass of Jupiter's moons, it's a small fraction of the total mass of the planet. So these are small moons, even taken all together. Jupiter itself is an order of magnitude or more short of having the mass to be a star. If you just piled mass onto Jupiter, just fed mass on top of the atmosphere, compressing it and heating it up, eventually you would reach a situation where Jupiter would ignite as a star. Arthur C. Clarke has written famously about this in his science fiction. But it's not a small amount of mass. Like I said, you'd have to multiply the mass of Jupiter out by a factor of 10 or more. So Jupiter's not in any way on the edge of being a star.
Ping Ponger would like to know, how do we know that black holes really exist and it's not just gravitational waves created by some other heavy celestial bodies like orbiting around themselves really closely?
And the best evidence for black holes, which goes back now to the 1970s, the first black hole to have convincing evidence in a binary system was Cygnus X1. I think the data goes back to 1969. So we know of about 40 or 50 black holes in binary systems, dead stars, where the binary orbit is so well measured, we know the mass of the dark or invisible object, and it has to be a black hole because that mass is more than 3.5 times the mass of the sun, and it's an evolved system. So those are the best evidence for black holes, and there's really no other simple way to explain those binary systems. The best evidence for any black hole at all, I think, is the evidence for the black hole in the center of our galaxy that was the subject of the winning of a Nobel Prize several years ago to Andrea Ghez and Reinhard Genzel. And that is based on the orbit of individual stars around the center of our galaxy, indicating a dark object about 4 million times the mass of the sun. Again, the concentration, the density of that mass driving those orbits in the speeds that we measure directly with Dopplership could not be explained by anything other than a black hole. So this is pretty compelling evidence for a black hole and not for any other phenomenon.
The next question is from KP, who's on with us live, who asks, since light travels faster than anything, and we use light for data transfer for modems here on Earth, could we use light to communicate with outer space vehicles? And I assume they mean visible light, because we already do sort of use light to communicate.
Sure. I mean, we tend to use radio waves to communicate with spacecraft and around the solar system, and that's simply because we have pretty sophisticated technology that goes back almost 100 years of how to code information in radio waves. Radio waves are fairly low energy waves, so they're easy or cheap to produce. We know how to imprint information on them by modulating their frequency or their amplitude. That's how you get AM and FM radio. So we've known how to do this for a long time, and that's why we use radio waves. Now, you could use light waves to communicate with spacecraft. The disadvantage of light waves is more energy is required because they're a lot more energetic. Their wavelengths are shorter and the energy is higher. Also, light is subject to scattering and absorption by dust, and there is dust in the solar system and in the near Earth. And radio waves essentially do not see dust. So that's the real big reason why we prefer radio waves.
The next question is from Nita Frank, who asks, does it make sense to look for life in the cracks of Europa since they're filled with frozen water from the subterranean oceans?
Well, there are all sorts of places we could look for life on Europa. It is true that the European ice, we very strongly suspect, is shifting over time. It's cracking and freezing. Water upwells into the cracks and then freezes as soon as it gets anywhere near that cold vacuum of space. But because of that cold vacuum of space and the cosmic rays there, life is very unlikely to exist near the surface of Europa in that upwelling water that immediately freezes. The best bet for life on Europa is, of course, deep in the ocean itself, under that ice cap, and probably even near the bottom of that ocean, where there's tepid heating from geothermal geological activity. And you need some energy to drive life. And so the warmest place on Europa is at the base of the ocean.
The next question is from Nashon Adero, who would like to know, any prospects in medical research from the adaptability of tardigrades? I hear they can survive everywhere, even in space. What can space explorers learn from the uniqueness of tardigrades?
Yes, tardigrades are indeed amazing. They're colloquially called water bears. That kids study them in their biology classes sometimes. So they're small. They have their own phylum in the tree of life, which is to say there are dozens, maybe hundreds of species. They're about 1/10 of a millimeter, pretty much the head of a pin. But they have legs. They have internal organs. I mean, they are genuine animals, very small, and they have survived in space, including outside a spacecraft and in the depths of space for significant time. The way they achieve that and the method by which NASA and other researchers are studying them is called cryptobiosis, which is their ability to roll into a sealed, hardened shell called a ton, and then take their fluid level down to about 1% of the normal level. So they essentially they're sort of freeze drying themselves, if you like, going into this anhydrous state. And within that state, they go into the form of suspended animation. We don't know exactly how they do it. As I mentioned, NASA is actually intensely studying tardigrades to try and get tricks of how we might, with humans, do this as a way of getting to the stars.
The next question is from Nita. In the supplementary reading, I saw that magnetic forces are only on the side facing the sun. Is that correct? I assume they mean on Earth.
Yeah, well, the sun emits high energy particles as well as the solar radiation that keeps us all alive and life on Earth sustained. And those high energy particles interact with the Earth's magnetic field, and that's how you get aurora. That's how you get interference of electromagnetic communication and sort of mayhem with mass telecommunications on Earth. So it is indeed on the sort of sun-facing side of the Earth that the interaction of the solar wind with the Earth's magnetic field is the strongest. But the Earth's magnetic field, of course, extends all the way around the Earth.
Excellent. The next question is from Sunaya. Why do we assume water to be a biomarker when we can't possibly guess biological components of other hypothetical beings?
It's true that we don't know what the basis for biology elsewhere in the universe might be. However, we do know that all biology on Earth, all living creatures on Earth use water at some level. The wettest living creature might be a jellyfish, 99% water, and the driest animal certainly would be a beetle with 30% water. They all have water. And so we think water is the medium for life. It's the medium that dissolves the ingredients and lets them interact and gain in complexity. And so biochemistry is heavily based on water. Doesn't mean it has to be elsewhere, But we also know water is a fairly abundant ingredient in the universe. And we know there are water worlds and habitable planets where water could be liquid, given their distance from the star and the brightness of their star. So it's not a stretch to look for water-based life because we know the water exists elsewhere. And of course, life on Earth heavily uses water and essentially can't exist without it.
The next question is from Rentgen 101. What is the smallest time increment that an electron or a particle can act on itself, I guess, or on anything else? I mean, really, this is about time. What are the smallest increments of time that the universe can know and interact with itself?
So the question, I mean, the deep question underlying the question that was asked is, of course, is time quantized? Since we know space is quantized, and Einstein produced a beautiful theory to show that space-time is a hyphenated entity, and space and time are coupled in very profound ways, and we see that. It is logical to ask whether time is quantized too, and at that level, we'd have to ask how particles behave when we take the increments of time down to the level that time might be quantized. So at the moment, no lab experiment or physics experiment has ever observed the graininess of time, if you like, or sort of fundamental unit of time, or an indivisible unit, or quantum of time, to analogize with quantum of energy. That doesn't mean that it doesn't exist. It's just at a level well below our capabilities of experimentation.
The next question, Real Opinions just wanted to say that it was nice meeting you at South by Southwest. So apparently they were there at that event.
Okay, that was fun, yes.
Ron would like to know, are there currently any attempts to build dark matter detectors like LIGO for gravitational waves? Are there attempts to build dark matter detectors sort of like LIGO detects gravitational waves? And if so, how do or would they work?
Well, there are dark matter detectors, and there's probably 24 physics experiments around the world that are actively trying to detect dark matter. Most of them are in mines or deep underground to remove the contamination from cosmic rays or high energy particles. And since dark matter is believed not to interact with photons or experience the electromagnetic force, the way these detectors typically work is they're looking for literally for collisions. They're looking for kinematic effects where dark matter plows into a liquid or a solid medium and gives energy to the lattice or to the medium, and you detect the energy delivered by a collision with a dark matter fundamental particle. So that's really the way the dark matter is being sought. It's not been found yet. Dark matter is, of course, dominant ingredient of the universe, but the density of dark matter in an average region of space is low. And so these collisions, if they occur, will occur at a very low frequency. And that's why you need huge underground experiments to detect them. So far, no events have been detected convincingly.
Terang would like to know, can we measure the curve, I assume they mean space-time curve, near two neutron stars when they are collapsing?
If by collapsing you mean colliding, then yes, we can. And LIGO has detected neutron star collisions as well as black hole collisions and an occasional black hole neutron star merger. So yes, when neutron stars collide, we can absolutely detect the perturbations or ripples in space-time with gravitational waves. We also see an enormous electromagnetic signal. It's now believed that roughly 1/3 of the heavy elements, the precious metals, and even the rare earths are generated in neutron star collisions. So it's not just gravitational waves, there's also a huge electromagnetic radiation signal and the creation of heavy elements from neutron star collisions.
So KP has a question, and my hypothesis is that these kinds of questions come from a misconception based on how we draw black holes. So the question is, what could be the end of a black hole? And I think it's because it's drawn often as that two-dimensional cone where something like goes in, and
Right.
the idea is the black hole is somehow the end of the pipe and not. But can you talk about what could be at the end of a black hole, and maybe how that misconception comes around?
Right. As a way of visualizing curved space-time, people tend to use the analogy of like a rubber sheet, where the black hole or the massive object curves, bends the rubber sheet, and a black hole represents an extreme curvature to the point of pinching off a piece of that space-time, or that two-dimensional surface. But that's not the universe we live in. The universe we live in is three-dimensional space, and so it's a harder concept. You imagine now that the pinprick pinching off of space-time, the singularity, is occurring in the middle of a three-dimensional object, a sphere, and that place is invisible to you because of the event horizon. So that's the better analogy. I think the two-dimensional analogy is just very limited for black holes.
The next question is, what are the pros and cons of having a space observatory in space where scientists could live and observe?
I think there are more cons for a living observatory in space than there are pros. And that's just because humans have enormous demands when they're in space. So keeping humans alive requires protecting them from the harsh environment. It requires feeding and watering them. It requires being able to give them medical attention if they need it, and getting them back to the Earth occasionally, and dealing with their psychological needs. So these are all demands that would be placed by an observatory in space that was staffed by astronomers or telescope operators. So the simple truth is that robotic observatories are far more efficient, they're far cheaper, and actually they work better than observatories staffed with people. And most of the world's ground-based telescopes are now operated robotically.
The next question is from Yang, who asks, is a black hole named after blackness in the visible spectrum? I saw that Einstein used gamma to denote light in a gravitation paper after the relativity theories. So is it only black in a visible light?
Yes, black hole is, of course, a reference to a visible phenomenon. But the true definition of a black hole is the existence of a region, the event horizon, from which no information can escape. So the better way of thinking about a black hole is an information trap rather than a light trap. Yes, it's true that light can't escape, and so it will look black if you're looking visibly, but it will look black in radio waves too, even though we can't see radio waves or any other electromagnetic wave. But more fundamentally, no information can escape, no particles, no other forms of information. And that's the better way to think of it, I think.
All right, we are almost out of time. I think we barely have time for one quick question here. So we'll take this last one from Dennis. Is the Higgs boson a particle or a field or a duality of the two?
I think more accurately, the Higgs particle is a field. It tends to get spoken of as a particle because I think that's easier for the average person, members of the public, to understand. And indeed, it has an equivalent energy. It has a resonance where it was detected at CERN, and that energy could be converted into an equivalent mass. So you can talk about it as a particle. But fundamentally, it's a field because it's the mechanism by which objects of any kind, fundamental particles, have mass. And it's those particles existing within this field and the viscosity or the friction, if you like, within that field that gives the different particles their different masses. So I think more accurately, and certainly in the math of working with the Higgs theory, it's a field. So that's a good question to end with. Thanks again for good variety of questions this week, some very interesting ones. And I think I'm back from Italy in a week or so, and I think we have the first one scheduled after my turn, but I can't remember when it is off the top.
That's correct. It's October 4th. The next one will be October 4th.
October 4th, and I'll be back from Italy. So I look forward to joining you all again then, and thanks, Matthew, for facilitating.
Excellent. Take care, everyone. We will see you again. Make sure that you like and subscribe to our channel so you can hear about announcements for upcoming live sessions. Take care, everyone.